Hello, my name is Steve Ives and I'm with the Synergex Professional Services Group. I'd like to welcome you to this presentation entitled Synergy Objects Part 2. This presentation, which is the second in a series of 3, is geared towards Synergy developers who wish to begin learning about object-oriented programming in Synergy, or towards developers who have experience developing with another OO language and want to learn how to use the OO techniques that they're already familiar with in Synergy language. This presentation is approximately 25 minutes long. If at any time you wish to stop and resume viewing at a later time, use the table of contents on the right to select the appropriate slide when you return. In Part 1, we introduced several OO terms and concepts. We then went on to introduce the Synergy language syntax for defining namespaces and classes and adding 3 types of members to those classes: fields, methods, and properties. Then we examined how objects are instantiated by declaring object variables and by using the new statement. In this presentation, we'll introduce some more new terminologies and concepts, and again we'll then go on to examine the Synergy language syntax, which allows us to use these techniques in the classes that we write. In particular, we'll be exploring the concepts of method overloading and examining how we can use special constructor and destructor methods to perform initialization and cleanup operations in the classes that we write. We'll also introduce static members. Our first subject for today is that of method overloading, which is a very common practice in object-oriented programming. Method overloading describes a situation which occurs if a single class includes multiple methods which have the same method name. Such methods are said to be overloaded. Essentially, there are 2 or more alternative implementations of the method present in the class. Typically, overloaded methods provide alternate ways of performing some operation, typically based on different input parameters. In fact, in order to overload a method, it's a requirement that each of the overloads has a unique parameter list when compared to its peer methods. When a class includes an overloaded method, the specific method to be executed is determined by comparing the parameters passed to the signatures of the various overloads. The method which is the best match to the supplied parameters will be the one selected for execution. For example, let's consider a customer class which includes an overloaded loadCustomer method. The fact that it's an overloaded method means that there are multiple methods with the same name in the class, each having a unique parameter list. In our example, we have one loadCustomer method which accepts a single alpha parameter, a customer account number. A second loadCustomer method also has one parameter, but this time that parameter is decimal and is used to pass a phone number. And a third loadCustomer method has 2 parameters, both decimal this time, allowing us to pass a zip code and the last 4 digits of a social security number. These overloaded methods provide consuming applications with 3 different ways to locate and load a customer, by providing either an account number, or a telephone number, or a combination of zip code and the last 4 digits of a social security number. Here you can see what the example on the previous slide would actually look like in code. As you can see, the 3 methods all have the same name and in fact the same return type, but each has a different parameter list. LoadCustomer is an overloaded method. Remember that when a piece of code actually calls the loadCustomer method, the compiler will compare the passed arguments to the argument lists of the various overload methods in the class and select the best match. Here we can see a piece of code which is actually using the overloaded method. You'll notice that obj is an object variable which refers to an instance of the customer class. The code then shows calls to the various overloads of the loadCustomer method. The first call passes an alpha, a customer account number. The second passes a single decimal, which must therefore be a telephone number. And finally, a third call passes 2 decimals, presumably a zip code, and the last 4 digits of a social security number. That's it. It's simple really. Overloaded methods give us a way of providing similar functionality based on variations of input data. Of course, when you think about it carefully, similar results can also be achieved using optional parameters and a single method. However, in some environments, including the .NET environment, the concept of optional parameters really doesn't exist, or at least doesn't exist in a form that we're used to working with in traditional Synergy applications. Avoiding the use of optional parameters will certainly help ensure that your code is more compatible with other environments in the future, other environments that you may well wish to use with your applications. Also, routines which rely on optional parameters will almost certainly be more complex to write and to maintain, because they need logic to determine which parameters were passed and therefore what actions to take in any particular instance. And in many cases, this logic can get quite complex. Using overloaded methods does mean having more methods in your class, but typically the code in those methods is much simpler to write and therefore is less prone to errors and of course is easier to maintain as well. In the first part of this series of presentations, we briefly introduced the concept of constructor and destructor methods, but we didn't really explain much about what they are, and we didn't explore how to define such methods in Synergy at all. Now it's time to delve a little deeper into this important aspect of object-oriented programming. So, what is a constructor? A constructor is a special method which can be included in a class. A constructor is executed automatically whenever that class is instantiated, or in other words, whenever an object of that type is created. Constructors are typically used to perform initialization within the object being created, perhaps by calculating initial values for some class fields, or possibly through doing things like opening data files. Constructors can have parameters defined. Declaring parameters in a constructor allows consuming routines to provide information that can then be used to initialize the new object. Constructors can also be overloaded. In other words, a class may have several constructors with different parameter lists. A calling routine can then determine which constructor is used for any given instance by passing different variations or different combinations of parameters when the new statement is used. By way of an example, consider a customer class. The class might have a constructor with no parameters, which would initialize a new or empty customer object, whereas an overloaded constructor may have a parameter which accepts a customer code, which would result in the new object being instantiated and initialized to contain data relating to that existing customer account. Constructors are easy to define. Essentially, they're similar to any other method in the class. The thing that makes a method a constructor is that the name of the method is the same as the name of the class. Another requirement for a method to be a constructor is that the method may not have a return type specified. With regular methods, you must declare the return type, even if that return type is specified as void, indicating no return value. With constructors, you simply don't declare a return type at all. In the code on the slide, you can see a customer object being instantiated. There are no parameters following the class name, so the constructor which accepts no parameters will be executed. On this slide you can see an example of a class which declares a constructor. It's a constructor because the name of the method is order, which is also the name of the class, and there is no return type specified. Notice that the method has no parameters, so it's replacing the implicit default constructor. This custom constructor sets a default value for the private variable discount. Also, note that the constructor is defined as public. It's a requirement, in fact, that all constructors must be declared as public. Here, on the left of the slide, is an example of a class which has two overloaded constructors. The first constructor has no parameters and sets the default discount to 5%. The second constructor has a decimal parameter and allows a consuming routine to actually pass the discount percent to be used at the time the object is instantiated. On the right side of the slide, you can see an example of a piece of code which is instantiating order objects. The first new statement does not pass any parameter, so the default constructor, the constructor without any parameters, will be used, causing the order to default to a discount of 5%. The second new statement, however, passes a value of 10. This means that the constructor with a single decimal parameter will be used, causing a discount of 10% to be applied to that order. By default, each and every class that you define will have an implicit default constructor. In other words, a constructor with no parameters. This default constructor doesn't actually do anything. It's simply present so that objects may be constructed with the syntax that you see on the slide. In other words, an empty set of parentheses. What you need to know is that as soon as you explicitly declare any constructor in your source code of the class, the compiler will no longer add an implicit default constructor. So, if you add a constructor with one or more parameters, but still want to be able to instantiate an object without specifying parameters, you must also add a constructor without parameters to your code, even if it doesn't do anything. Destructors are kind of the opposite of constructors. Again, they're special methods which are called when an object, this time, is deleted. Destructors are generally used to clean up any resources which may have been allocated during the construction or during the use of the object. For example, a destructor might be used to close data files, deallocate dynamic memory, or dereference other objects which you may have handles to within the object that's been deleted. A class can only have one destructor, and because the destructor is called automatically when an object is being deleted, it can't have any parameters defined. A destructor is again just a method in a class, and, as with a constructor, it's a naming convention which identifies a method as a destructor. The name of the destructor method is the same as the name of the class, but this time prefixed with a tilde character. Destructor methods may not have any accessibility or indeed any other method modifiers specified, and may not have a return type or any arguments defined. Remember, if a class has a destructor method defined, then that method is executed automatically when an instance of that class, in other words an object, is being deleted. In the example code at the bottom of the slide, you can see that a customer object is instantiated and then dereferenced. Because there was only one reference to the object, its reference count will fall to 0 as a result of the clear statement, causing the object to be deleted. As part of the deletion of the object, the destructor would execute. This slide shows an example of a class called order, which includes a destructor. As you can see, the name of the destructor method is tilde order. Also notice that there are no modifiers specified on the method, no return value, and no parameters. Some OO languages have support for another kind of special method called a finalizer. Finalizers are similar in concept to destructors. The difference lies in when the method is called. Typically, a destructor is executed as soon as an object is deleted, whereas a finalizer is executed sometime after an object is deleted, typically during a garbage collection operation. This subtle difference can be important to an application because it may mean that resources are not freed immediately, which may or may not be a problem. Currently, Synergy does not have support for finalizers. However, when Synergy DE4.net is introduced, it's likely that destructors will become finalizers in that environment. Clearly, this means that the deallocation of resources could be deferred until a later time, which in turn may impact the way your applications behave when executed in the .NET environment. If you do intend to write Synergy OO code that will, in the future, execute under the .NET runtime, then it's important, and if it's important to you that resources are freed at a specific known time, then what we'd recommend is that you don't use destructors to perform cleanup operations. Instead, add your own method to your classes and explicitly call those methods before you delete an object. This is a quite common technique, and very often programmers would call such a method dispose. Now we'll move on to examine another capability of object-oriented languages, the ability to declare static members. We'll look at what the term static means, and then explore the different types of static members that can be defined in your classes. So far during these presentations, we've looked at three main types of the members of a class: fields, methods, and properties. All of these members have been what are known as instance members, and what this basically means is that in order to access the member, an instance of the class, or in other words, an object, must exist. Essentially, instance members can only be accessed via an instance of the class, via an object. Static members are altogether different in that they can be accessed directly via the name of the class, without having to first create an instance of the class. In fact, static members can only be accessed via the class name, not via an object. Because of the way that static members are accessed, they're sometimes also referred to as class fields, class methods, or class properties. First, let's look at static fields, which are fields which are defined at the class level and are accessed via the class name. The important thing to realize about static fields is that there is only one field, which is part of the class. Regular fields are considered instance data. In other words, each object has its own copy of each field. With static fields, there is only one field existing in memory. Essentially, all instances of the class share that same static field. In some ways, you can consider static fields to be similar to traditional static records in Synergy. The difference is that traditional static records are shared by multiple instances of a reentrant routine, whereas static fields in a class are shared by all instances of the class, or all objects of that type. Like instance fields, static fields can be declared with public or private accessibility. Public static fields can be accessed from anywhere, whereas private static fields can only be accessed from within the same class. At the top of this slide, you can see an example of a class with a static field called confirmDelete. Notice that the field is public. At the bottom of the slide is an example of the static field being referenced. Notice that the code accesses the static field directly via the class name. There is no new statement to create an instance of the params class involved here. No object being created. Static fields are accessed directly at the class level. Static methods are methods which exist at the class level and are called via the class name, not via an object variable. Again, it's not valid to execute a static method via an object, only via a class. There are some special rules that you must follow when writing static methods. For example, you can define data locally in the method, and you can access static members within the class, but you can't access any non-static members, because non-static members require that an object is created, and static methods are executed without the presence of an object. Static members can be a difficult concept for beginners to get to grips with, but they can be very useful. For example, for methods which are completely stateless, using static methods can often be appropriate. One common use of a static method is for something called a factory method. This will be a method which is called via the class name and is responsible for constructing and returning a new instance of the class. Often, applications may have a set of generic utility methods which are frequently used. Making such methods static means that they can be easily accessed and called from anywhere without having to instantiate or propagate objects. On this slide you can see an example of a static method. The class is called file, and the method is a public static method called rename. It renames a file. Remember, public means can be accessed from anywhere, and static means without first creating an object. This method simply renames a file and performs basic error trapping using a try-catch statement. Here is some example code which uses the class and static method from the previous slide. Notice that we haven't declared an object variable, and we haven't used a new to create a file object, because the rename method is a static method, and we can simply call it directly via the class name, file.rename. The third type of static members are, of course, properties. Similar to fields and methods, static properties are accessed via the class name and have similar restrictions to static methods. Local data can be used in the get and set methods, but any instance members of the containing class can't be used, only other static members. Why use static properties? The most common case is if you need to control access to static fields, much like using non-static properties to control access to non-static fields. Here's an example of a class called params, which has a read-only public static property. The property is used to control access to the private static field. Remember, the property is read-only because it does not have a set method. Here is an example of a class with a public static field called instance count. Basically, you can use it to find out how many instances of the class there are out there in your application. The class has a constructor which increments the static variable. And the class also has a destructor which decrements the static variable, meaning that as objects are created and deleted, the value of the instance count public static field is incremented and decremented to reflect how many objects are out there at any point in time. This code will work, but there is a potential problem. The static variable is public, so other code could use it not only to determine the instance count, but there's nothing stopping any other piece of code in the application from actually changing the value, which kind of defeats the point. So what we could do with is a slightly better solution. On this slide we could see a better solution. In this class we've changed the variable used to track the instance count to now being a private static variable, which means that we can use it internally, but external code can't mess with it. We still have a constructor which increments the instance count, and we still have a destructor which decrements the instance count. But this time we've exposed the private static field, which now can't be accessed outside of the class, via a public static read-only property. This gives us a perfect solution because we can control access to the variable that we're using within the class, and we can expose access to that variable in a read-only fashion using a read-only property. Again, remember the property is read-only simply because there is no set method present. While we're on the subject of accessibility of data, version 9 introduces two new types of fields or records, but these are only supported within classes. CONST data is data whose value can only be set with an initial value specification, and the value can't be changed at any time from anywhere. By default, because CONST data can only ever have one fixed value, CONST data is also static, meaning there is only one copy of the data which is shared between all instances of the class. We also now support read-only data, which is data whose value can only be set via initial values or in the constructor of a class. Once set, the value cannot be changed from anywhere. Read-only data is not static. each object has its own copy of the data because the values may be different for each object, depending on what code executes in the constructor. On this slide, you can see an example of declaring some const data. As you can see, you can declare const fields or const records. If you declare a const record, then all fields within the record are also const. Remember, the only way to set the value of a const field is via its initial value specification. And here is an example of read-only data. In this case, a read-only record containing several fields. In this example, the data is being populated by a read statement from an ISAM file in the constructor. After the constructor is executed, the record is then read-only from everywhere. Well, that about wraps things up for this session. In this session, we've introduced the use of method overloading. We've also talked about constructors and destructors, and most recently talked about static members. In the next presentation in this series, we'll introduce the subject of inheritance.